All right, hello class. So this lecture is going to be a synthesis of the materials that you are covering for the lesson on global climate change. Global climate change is a small segment of chapter 2. We are going to dedicate more time and additional materials beyond your book to this lesson, given that it is such an important contemporary global issue. Okay, so here's an outline of the lesson. So the basic key terms, basic science, the scientific consensus is what this lecture is going to cover. And you will continue the lesson with looking at patterns of CO2 emissions throughout the world, looking at the consequences of climate change, and the ways that we can respond. So when we talk about responding to climate change, we're going to pay specific focus to what Europe is doing as we transition into chapter 8. We need to differentiate a couple of terms when talking about climate change. One, it's weather, right? So weather is atmospheric conditions at a given place and time. It depends on temperature, moisture content, winds, and precipitation of a particular day or time, right? So for example, in Fullerton today, what is the temperature? What is the relative humidity, the winds? Are the skies clear today? And certainly that may vary what happens in the morning and in the evening. So meaning weather is something that changes often, and it is short-term patterns of atmospheric conditions. Now that differs from climate, okay? Climate is an area's long-term atmospheric conditions. So looking at over 1 year in Fullerton, what does temperature and precipitation look like, not just quantitatively, right? What were the highs and the lows and the average, but also qualitatively, right? When did it rain? How much did it rain? So on. So it's a mixture of quantitative and qualitative observations, okay? So climate, or this the long-term patterns of weather, right? What kind of weather you can expect in place in the world given the history of weather in those places. It's essentially affected by three things, okay? So the sun, or not necessarily the sun's variability, sure, but also, or most importantly, our relation to the sun, where we are in relation to solar radiation. So as you learned in chapter 2, if we are in places of the earth that receive more direct solar radiation, such as the tropics, climates are therefore experiencing warmer temperatures in those places. Okay, so atmosphere, what is the composition of the atmosphere is absolutely important in climate, pressure cells, and so on, and oceans, okay, as you learned in chapter 2. Now, global climate change, okay, describes the trends and variations in the Earth's climate. So when you look at long history, right, and we're not talking about just a couple hundreds of years, we're talking about thousands of years or hundreds of thousands of years, and looking at the variations in Earth's climate throughout time. Okay, so looking at temperatures and precipitation patterns, frequency of storms, and so on. Okay. Global warming, on the other hand, refers to an increase in the Earth's average temperatures that we are particularly experiencing right now. Okay, so why is it important to talk about these terms? Well, because essentially you can't walk out one day in Fullerton that is 105 degrees and say global warming is real, right? Because that is an observation based on one day. Climate, and when we're talking about an overall temperature increase or overall average temperature increase over time, we're talking about long-term data. We're talking about observations in the Earth's climate and looking at how the Earth's climate has behaved based on the data that we have, and how currently, when looking at that history, what we are seeing is that the Earth's average temperatures are increasing. Okay, now this is important, and you also realize how the language has changed It is true that the Earth's average temperatures are increasing. Nonetheless, what you are seeing is that scientists are increasingly, or even media and educators are increasingly use the term global climate change, because it is important to note that as the Earth's average temperatures rise, that may not necessarily mean for certain places in the world that they will not have cooler temperatures. So for example, I'm going to show you in one instance, looking at Europe, for example, how an increasing average temperature may mean cooler temperatures for a period of time in some places. Okay, so I guess the key term here is average, right? So average temperatures do not mean that there aren't higher and lower temperatures. It just means that when you gather all of the data, that on average the temperatures are rising. Okay, so those are the four important key terms that you need to know. So climate change is complicated. It is a complicated phenomenon, but it is also very simple in the fundamental science, right? The fundamental process that helps us understand how how climate works and how the atmosphere interacts with solar radiation. And this fundamental process, this natural phenomenon, is called the greenhouse effect. And in understanding the greenhouse effect, you should understand how the composition of the Earth's atmosphere shapes climate, okay? I posted a resource for you, a PBS NASA collaboration video. I recommend that you watch that first and see that after watching that, you should be able to understand this diagram very well. So in this diagram, essentially is telling you that the Earth is enveloped in this gaseous sphere, the atmosphere, and this gaseous sphere has a series of gases that interacts with solar radiation or radiation in general. When it comes to solar radiation, the sun emits shortwave radiation towards the Earth, and some gases in the atmosphere reflect, in particular like clouds, right, reflect a lot of the incoming solar radiation. Some of these rays are bad for us, like UV, for example, and a lot of that is filtered out by the atmosphere, making about 50% of solar radiation able to penetrate the atmosphere. Once that 50% of solar radiation penetrates the atmosphere, it is absorbed by planet Earth, in which planet Earth re-emits that radiation in long wave radiation. This long wave radiation is essentially heat. This makes sense. In your daily experience, you can see this because what is the hottest time of the day, for example, right? We know that here in Fullerton, the sun is at its highest at noon. Nonetheless, the time that it is warm is not at noon, it is around 3 or 4 o'clock, right? And that is because of that delay. While the Earth has received that noon solar radiation, it absorbs and re-emitted in the form of heat at about 3 o'clock, okay? So when you look at long wave radiation, it also interacts with gases in the atmosphere, and these are greenhouse gases like water vapor, carbon dioxide, which trap this heat and keep about 90% of this radiation into the lower atmosphere. So it sort of just bounces back and keeps the Earth warm. As you learn from the video, this is a natural phenomenon and essentially makes life possible on Earth. So what are these greenhouse gases? Okay, so greenhouse gases, once again, are gases that absorb infrared radiation very effectively. Water vapor, carbon dioxide, nitrous oxide, methane, and CFCs, for example, are uh, all greenhouse gases that absorb this long wave infrared radiation or heat very effectively. But out of all of these gases, okay, they all have different global warming potential, or essentially their ability to trap heat varies. One molecule of methane, for example, is better at trapping heat than one molecule of carbon dioxide. So let me explain. If you look at carbon dioxide, what this table is telling you is that if carbon dioxide has the ability to trap heat equivalent to 1, methane is 23 times more potent than carbon dioxide at trapping heat. Nitrous oxide is 296 times more potent, and hydrofluorocarbons is 12,000 times more potent. So essentially, what we have most abundant in the atmosphere is water vapor and carbon dioxide, but nonetheless, when we look at the emissions, which one is it that we emit the most? Carbon dioxide, by far, is the greenhouse gas that we emit the most. So you may be wondering, if methane and nitrous oxide and CFCs are so potent at trapping heat, why is the conversation most often dedicated to carbon dioxide? Well, the conversation should be and is dedicated to other greenhouse gases. For example, the Montreal Protocol focused mostly on this gas here. And but nonetheless, because we emit carbon dioxide the most, overwhelmingly more, and because we emit carbon dioxide through burning fossil fuels, a lot of attention is dedicated to carbon dioxide because of its abundance and because we emit it more than any other gases. So how do we know that current CO2 concentrations or other gases are the concentration of other gases, but in particular CO2? How do we know that it is currently an excess compared to natural variability? The Earth's history is, a 4 billion-year-old planet. Our industrial society is hundreds of years old. How could we, in such short period of time, have such an immense impact? Have we? And how do we know that? Well, there are multiple ways of learning from the past. Of course, the physically collected data, like from satellites, for example, are fairly recent. But interestingly enough, the planet in itself records data about CO2 concentrations. You can learn about the past by reading the chemical composition of some rocks or lakebed sediment. You can learn about the composition of the Earth's atmosphere from thousands of years ago by looking at tree rings. Some trees, like for example, Bristol cone pine is 4,000 years old. So we can go back through the data and go back through these natural data reservoirs and make observations about the Earth's atmosphere from a time that predates or scientific inquiry about climate. So in particular, I'm going to tell you about one piece of data, and that has been ice. So looking at ice and essentially drilling ice layers over time, right? And meaning that in some places you can go deep enough to get ice that is as old as, 600,000 years. And why is ice so telling? Well, ice is telling because it captures small bubbles, right? And these small bubbles are essentially samples of the Earth's atmosphere of the past. So I'm going to take you to this resource here, this NASA resource. See if it takes us there.
Locked in a warehouse-sized freezer in suburban Denver, the Earth's climate history. Thousands of years trapped in gases, acids, dust, water molecules, and atoms.
It doesn't hit me like some people see it. It's like, wow, this piece of ice is 400,000 years old. Well, to me, it's a very valuable piece of ice, and it's my job to make sure it stays that way.
The priceless treasures are all stored here, the National Ice Core Laboratory, home to 17,000 meters of ice collected from around the world, stored at negative 33 degrees Fahrenheit. This summer, the lab received an ice core drilled at the South Pole. Working in a relatively comfortable minus 11 degrees Fahrenheit, researchers cut the ice, catalog the depth, photograph it, and conduct preliminary tests. Here, a college student shoots a jolt of electricity through a piece of ice as a University of Washington researcher watches the results on a computer.
Hey, we got a volcano.
The electricity detects a layer of acid in the ice deposited by an eruption long ago.
That is a big volcanic event that occurred about 8,000 years ago. We can actually figure out how much volcanic activity there's been through time to help understand how the climate system has worked.
Scientists also take thin slices and look at the crystals through a special light. Samples are cut and packed for shipment to other labs, including the Institute of Arctic and Alpine Research in Boulder, which constantly monitors air samples from around the world.
Ice cores are a great proving ground for models that can predict climate in the future.
Bruce Vaughn says heavier oxygen molecules in the ice from ancient snowstorms indicate warmer temperatures. To get that information, Vaughn melts the ice millimeter by millimeter.
What we have is a really pretty accurate historical thermometer. It's as if we were standing on the ice sheet writing down the temperature for the last 800,000 years.
Scientists continue to find new ways to study the past, including analyzing trace gases to learn about the amount of previous plant life on Earth.
Bubbles that are stored in the ice are now escaping in this debubbler for the first time.
Each piece of ice helping to unlock mysteries frozen in time. Peter Banda, Associated Press, Lakewood, Colorado.
So that is how scientists are able to look at ice. Pretty fascinating science. And let's play scientists here by looking at what these ice cores tell us. Play scientists by looking at, can you read this data, right? So here's the data that we've learned from Dome Sea, Antarctica, which is the deepest ice core ever, revealing, 10,628 feet of ice, but most importantly, giving us the longest data string ever. So take a look at this graph here. And if you need to pause the video, do so that you can digest the information that is here. There are 3 findings that you should be able to come up with looking at this graph. What are these 3 findings? The first finding is that what you can see is that carbon dioxide and methane have varied, the concentrations have varied over time, that there are natural fluctuations of greenhouse gases, or if we look at carbon dioxide alone, that has varied over time. Another observation that you can make is that temperature swings as well. The temperatures that the Earth has experienced various temperature swings or variations over time as well. And that these temperature variations correlate with the concentrations of greenhouse gases. Generally speaking, when greenhouse gases are up, temperatures are up, which makes sense with what you understand about the greenhouse effect. And the third observation that you can make is that when you look at over time, right, when you look at the longest data set that we have, that today's concentrations of greenhouse gases of CO2, and our current 2016 concentration is actually even higher than this, that today the concentrations do not fall within natural variability, that we have unprecedented concentrations of both CO2 and methane, which is off the charts. So NASA reports this well. You can see if we isolate carbon dioxide alone and we look at the centuries and the thousands of years that carbon dioxide has stayed within, this is what natural variability looks like without industrialization, right? And here is where we are now. Here is where we were in 1950. Those concentrations are increasing or have increased dramatically, in particular in modern times, okay? So what is too much? When I was in college, in grad school in particular, I remember attending seminars asking that question, what is too much, right? And too much was 400 parts per million, saying, I remember having seminars about when the earth reaches 400 parts per million concentration of carbon dioxide, that the earth is going to change dramatically. And then I started teaching, I graduated college, and then in 2013, it happened. The earth reached 400 parts per million for the first time. Now, 400 parts per million was reached in 2013. In 2016, that is our average, right? So the earth's average is now at, I believe, 406, or getting close to 406, and it is estimated that we will keep on climbing. So 400 parts per million mark is what they call a threshold, a benchmark, a time in which scientists had feared that the earth would change dramatically, and it already has. So knowing that the foundation of the greenhouse effect, what you should gather is that more greenhouse gases, more trapping of heat, and increased average temperatures. And that's exactly what we are seeing. We are seeing a global increase in average temperatures. Here is looking at the 1800s and 2016 and seeing how that has gone up. And in particular, the past 3 years, 2014, 2015, and 2016 have been the hottest years on record, okay? So we keep on breaking record temperatures. Let me take you to this quick time lapse. NASA has this awesome visual here for you where you can see temperatures increasing, and note which places are experiencing the most increases, okay? And this is the increase of average temperatures, places that have experienced increases. So the last couple of years, what you are seeing is a lot of media coverage on global warming. These are clickable articles from the New York Times giving an analysis. The data in this particular map comes from NASA and showing you how the recent temperatures compare with the past. But most importantly, I think that the human experience of this, that a lot of the places that are experiencing the tremendous consequences of these changes are not necessarily the places that are emitting the greenhouse gases as much as the developed world or the industrialized nations of the world. But in any case, in particular, looking at, the heat waves in India, like this article does a good analysis of what's happening in India and how people are sleeping in rooftops and piling up in family rooms that have an AC, and that the purchases of air conditioning in places like India have increased tremendously. And the thing about these appliances that are being purchased in the developing world is that they're not the Energy Star appliances, the appliances that we are adopting in the developed world. We're talking about AC units that depend on coolants that are very old and inefficient, but most importantly that these appliances emit CFCs, which are the most potent greenhouse gas that exists. So how can we transfer technology in order to help the developing world adapt to these horrendous heat waves, that in an efficient way, in a way that, you know, doesn't worsen the problem. But another important pattern that you must know before we move on here is that as the earth warms, right, as average temperatures increase globally, it doesn't mean that some places may not actually get cooler. So here is a NASA image of global warm temperatures in 2015. And can you see some places here where temperatures have actually decreased? Okay, it should be evident to you that places in particular, you know, Antarctica and here off the coast of Greenland, the North Atlantic, has experienced temperature drops. Why is that? How is it possible in a warming world that the North Atlantic is actually getting colder? Well, essentially, this is the thing about science, you know, it validates itself with data, right? So essentially, there was a theory that came up in Nature magazine, and I believe the year was 2000. And the theory was that Europe would actually get colder. Some places in Europe, in particular, these places in Europe, would actually get colder as the earth got warmer. And the reason for this is what they described this Nature publication as the Big Chill theory. And the Big Chill theory essentially describes, you can read the information here in your PowerPoint file, but I'll just quickly explain. Greenland's ice melt has accelerated so dramatically, and that ice melt is constant, and that ice melt is creating a pool of cold molten ice, or a pool of cold fresh water right here in the North Atlantic. And that cool fresh water is slowing down a major ocean current, the Gulf Stream. And the Gulf Stream was a warm current that used to actually be a moderating force for Western Europe. And now, instead of receiving this warming or moderate water body through the Gulf Stream, Western Europe is now being impacted by a pool of ice melt, of cold ice melt. And that is how those temperatures are dropping, okay? So the last segment of this lecture asks the question, are we responsible for climate change? Okay, so there are a couple of resources for you to take a look at here. And essentially, there is one thing that I think is important when it comes to this question is, who do you ask, right? Who do you ask such question? I have students often ask me, Professor Gregorio, do you believe in global warming? And my answer is, it's not a belief system. It is not, I believe, I don't believe. Is your question really should be, what is the science on global warming? What are scientists saying about global warming, right? So there are a couple of bodies of science, right? Collective bodies of science. Is not one individual paper. We're looking at big collaboratory studies. And the big one here is the IPCC, or the Intergovernmental Panel on Climate Change. And essentially, this is a body of scientists, hundreds of scientists from all over the world, that unite every 6 years or so to revise the publication and create a single report. The last IPCC reports had 9,000 citations and included people from I think it was 36 countries or something like that. But in any case, what is the IPCC saying, right? If there's somebody who has a good voice on the issue, is this organization that is composed of global scientists reviewing a whole lot of scientific publications in order to inform the world on the issue. When I was in college, we worked with the 2007 report. In the 2007 report, IPCC stated that yes, the Earth is warming, and yes, we are 90% sure that it is due to human causes. Okay? The 2013 report was particularly important because there were 6 years of doubt. There were 6 years of you know, media's projecting a debate, and the 2013 report came with a very important role, and that is to really deliver the scientific expertise on the issue. So what did they say? Well, it was something they said was actually, you know, if you read the newspapers during this time, there was a whole lot written, and what was written was essentially, wow, this report is extremely detailed in its science, and it is the most inclusive report that IPCC had produced. But here's what they said that was different. They said the Earth is warming, and we are 95% certain that human activities are responsible. Okay, so human activities are the cause. 95% certainty. They increased their certainty from 90 to 95%, and that is a very high certainty for science. Okay, they also concluded in their reports that the concentrations of CO2 are unprecedented based on 800,000 years of data, that nothing like that has happened according to what we have, the data that we have. So some people say, okay, but the IPCC, hundreds of scientists do not represent the body of science. There are many scientists that are not in the IPCC, and the IPCC is a group of select scientific clique, essentially, and they don't represent the body of science. So some universities took it upon themselves to say, okay, we're going to, aside from the IPCC reports, we are going to look at independent publications coming from climate experts, and we are going to tally how many of those publications are saying that yes, global warming is happening, and yes, we are the cause. So here is here's a news article that came out in The Guardian in 2013 that details the scientific study. But here is essentially a graph showing you that this study and others, there are about 5 studies like this, confirm that there's an overwhelming consensus among scientists that global warming is happening and that it is due to humans. Okay, so if you look here, this is going to link you to the study. This links you to the news sources, but also is important to know that on a third point here, that 200 global scientific organizations endorse that humans are causing a global warming by emitting fossil fuels and enhancing the heat trapping abilities of the atmosphere. So all in all, I've told you 3 things. 1, the Earth is warming, that we have experienced the last 3 years with record breaking temperatures. That 2, it's because of us, because we are burning fossil fuels, we're adding greenhouse gases such as carbon dioxide. Other activities such as agriculture, as you'll learn later on, are responsible for more greenhouse gases to be added to the atmosphere. And this adding of greenhouse gases onto atmosphere is thickening the blankets that traps heat or enhancing the greenhouse effect. And yes, we are sure the IPCC reports the 97% consensus and the endorsement of human-caused global warming by over 200 scientific organizations puts great weight on the issue.